Okay, so this is a set of notes on ODEs, short for ordinary differential equations, and slope fields. Okay, so an ODE is essentially any equation that has a derivative in it, which makes it a little bit different. So if we have an ordinary derivative in the equation itself, it is an ordinary differential equation. If I want to solve an ODE, then an equation is the solution of this. So a typical equation is the solution. So like I could have something like 3 dy dx is equal to the natural log of x plus y. That would be an ordinary differential equation. Anything that would make this true, so some sort of equation that would make this true, is what we would call a differential equation. So let's give a more clear example here of what we're talking about. Let's just try something basic here, like y is dy dx. So what is an irregular equation that would solve this? Well, it's pretty trivial that y equals e to the x works here. Because if I take the derivative of y with respect to x, I get e to the x back, which means the derivative of y with respect to x is y. Okay, so this solves that ordinary differential equation. But see, the problem here is the solution is not unique, right? Like I also could say y is e to the x plus 4. Okay, so this also, when you take the derivative with respect to x, is just e to the x. Oh, wait, nope, that's not true. Okay, so this may beg the question, like, what is then a slope field? And how does this relate to ordinary differential equations? Well, essentially, let's look at a differential equation. Let's look at dy dx is x times y. Okay, a slope field is basically a way to graph this ordinary differential equation. So what I'm going to do is I'm going to build kind of like a grid of dots here. So I'm going to build a dot going up 1, 2, 3, put 1 at the origin, go over 1, 2, 3, 1, 2, 3, 1, 2, 3, and then we're going to put all the rest of the dots here. Okay, so these are somewhat tedious to draw, but they're pretty instructive once we get them. So we're going to build ourselves a plane of dots here. Alright, and there's actually like, sometimes you can go online, you can find like online dot paper, and it'll actually make that all easier, but for our purposes here, it's just good enough to draw these by hand. Now, what we want to look at is, if I were to put the locations of these dots in here, well, what would the derivative be? So, like, a logical place is that if either x or y is 0, then the derivative is 0, which means the slope of a solution has to be 0 at that point. So if the slope is 0, we're going to make a little horizontal mark there, because that's what slope 0 looks like. So at all the places where x and y are 0, we're going to put a little horizontal mark there. Okay, so that's accomplishing quite a bit of my grid here. Okay, so there we go. All these places are where x and y are equal to 0. Okay, so what happens here? Like if I take 1, 1, the slope is 1, so that's a positive slope. And if I take negative 1, 1, the slope is also 1, gives me a positive slope of 1. Okay, so going up, this is 1, 2. That's giving me a positive slope of 2. and the one above it is 1, 3, is a positive slope of 3, so we're getting steeper and steeper as we're going up. Same thing with as we're going out, so 2 and then 3, right? This is going to have a positive slope of, let's see, 2 times 2 is 4, right? 3 times 2 is 6, and then the slope out here is 3 times 3, which is 9, which is like really intensely up. Now if you think about this, down here in the lower right hand corner, these are going to go exactly the same. These are all, because this is positive times positive, so down in the right hand corner we're going to be negative times negative. So down here we're going to get the exact same values, but just negatively. All right, so this will have a slope of 2, this will have a slope of 3. Actually, same values, it's still positive, because negative times negative makes it positive. This is a slope of 4, a slope of 6, and ultimately down here, a slope of 9. Okay, so we've got that. The other two quadrants are going to mirror this, but this one is going to be negative, positive, so these are all going to be downward facing, right? So this is like a slope of -1, a slope of -2, a slope of -3, a slope of -4, slope of -6, and a slope of 9. And then here it's exactly the same as this. Slope of -1, -2, -3, -4, -6, and -9. Okay, so what is the point of this? A way to envision this is you take a small child and you envision this as a parking lot, okay? And you say, okay, if I take a small child and I put them down at some point on this parking lot and say just follow the lines, the child will actually know how to follow the lines, which means that the solution, or a solution to this, would be somebody following that pathway. Or let's say I put a child here, and I have them follow the lines, right? So there we go. It is likely that another solution to this differential equation would follow that pathway, or another one could follow this pathway, kind of coming up. So we get a sense of where would solutions to this differential equation lie in the plane. So remember, the solutions to a differential equation are not unique. And if I back this up a little bit, the slope field gives me potential pathways for solutions to ordinary differential equations. So in a sense, a slope field is a map of an ODE. Okay, so let's build a second example. Let's build something a little bit more complex. Let's go, don't need that, dy dx is cosine x. Okay, so the derivative is the cosine. Yeah, all right, so not too bad. The one thing to note here is that this is a trig function, so instead of going by ones, let's on the x-axis go like pi over 2, pi, 3 pi over 2, 2 pi. Coming back the other way, let's make it negative pi over 2. Okay, so negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. Okay, so we're going to make this 1, 2, 3, 4, 1, 2, 3, 4, and we'll put in the dots, right? So we're counting by ones and going over the y-axis, but we're counting by units of pi over 2 going over the x-axis. Okay, so I'm putting a whole bunch of dots here, making our grid. Now, an easy thing to note here is that this differential equation is only dependent upon the x variable. So the slope here has nothing to do with the y variable. So this is an interesting thing to notice, right? So it's only cosine x. There is no y in the differential equation here. So as we're figuring out slopes, it's pretty much you can go along one of the sets of x values, right, and then kind of work out the y's. So if you think about this, the cosine at 0 is 1, so my slope there is going to be 1. The cosine at pi over 2 is 0, so my slope is going across here. My slope at pi is going to be -1, back to 0, back to 1. 0, -1, 0, 1. Now, we've said that this is not dependent upon the y value. So every one of these going up and down is going to be the same. Kind of working that out. All of the, wherever x is pi over 2 is 0. Wherever x is 0, we get 1. Wherever x is, there we go, we're at 0 again. So that was -pi over 2. This is pi over 2, still 0. At pi, we're -1. 3 pi over 2, we're back to 0. And at 2 pi, we're again at +1. Alright, so this is the slope field that would be formed here. Now, like we said with the small child and like the tricycle in the parking lot, if we pick some place here, something interesting happens, right? So it kind of goes up and then down, and then back up, down, up, down. Aha, so the solution here, let's start one at 0. Let's see what happens there. It's a different color. Purple. There we go. Goes up, down, back up, and then down, up, back down. Aha, that curve is actually looking a lot like sine of x. And this one here, the orange one, looks a lot like sine of x plus 1. Okay, so that should make sense that a solution would follow the pathway given by the slope field, and if I took the derivative with respect to x of the sine of x, I get cosine x. Or if I take the derivative of x of the sine of x plus 1, I also get the cosine of x, which is the differential equation that this slope field should be mapping. Alright, so there's a little bit on ordinary differential equations and slope fields. You're going to get some practice with this in class. The best way to learn this is by practicing them. So, thank you.